Okay, folks, so this is the video for the first part of Mod 4. Mod 4 is on something called ANOVA, and you're like, that's kind of cool sounding. It is actually. What is ANOVA? ANOVA, essentially, in a nutshell, is an expansion of the two-sample t-test on means. And you're like, how? The limitation of the two-sample t-test is that you can only have two groups. We want more than two groups, but this test doesn't cover more than two groups. So ANOVA comes into play and takes over when you have three or more groups. Now, the way that it's run is really funny. This is not a technical course. This is the course for applied psychology students. So I have to explain this without like getting super like over techie on this. But so this literally is the expansion of the independent, not the dependent. Remember way back when in the first mod, there were two group tests for means for t-test. One was called the dependent test. That was when you had the before or after. That's not relevant here. What's relevant here is the two independent groups when you had like males and females, two independent groups. Okay. So ANOVA expands to more than two independent groups. Why is it called ANOVA? ANOVA actually stands for the analysis of variance. Yes, the same variance that you use when you calculate the standard deviation variability data set. However, I don't know who initially thought of this. It's a very bizarre test in the way that it's run. It's not super hard. It's just a really sort of odd test in that the metrics it's using variances to test means, and you're like, what? Remember though that the variance / standard deviation formula, everything is based on the mean. So when you have a standard deviation, or we'll make that a variance, well, sample standard deviation will make that. No, sorry, sample variance. The mean is always in that formula. So yes, the variance and the mean are related. So it's not as bizarre and weird as it thinks to be testing something and calling it the analysis of variance when it's really testing more than two mean differences. Okay. I hope that's clear. I do. Again, the algorithm of basic hypothesis testing is always the same. I made this slide once and it covers almost everything in the course. Really, it's kind of a nice course in the sense that it's really this one central theme for the most part, and we learn all these different kinds of tests and ways of assessing things that are relevant to psychology. So the hypothesis in ANOVA is always the same. The null is that the group means are equal. Now with two means, it would just be two, and then this expands to three or more, or you could technically test as many as you want with ANOVA. I mean, you can't get crazy overcomplicated. And the alt is that, now be careful about the alt. The alt is not that all of them are not equal. The alt is that at least one is not equal, okay? And this is actually going to become an issue. Okay? It's not that we're testing that they're all not equal. No. It's only that at least one of them has to be different. And then we're going to have to actually look and analyze that a little further. So it's kind of similar to what the two-sample t-test does. The test statistic is based on the data. We're going to look at this crazy distribution called an F distribution. Again, this is not the theoretical technical class. So for you guys, it's just like you should be familiar with like that. That's the distribution that's used for ANOVA. I don't want to get crazy distracted in like sort of mathematical minutia here. Okay. And then we determine from the data if the claim is supported using the test statistic, which is an F stat in this case. Okay. And that's the basics of ANOVA in a nutshell. There's going to be 4 videos. I just decided that. I sat and reviewed everything. Like 4 is a good number. Okay. So ANOVA, as mentioned, used something called the F distribution. The first continuous distribution uses the normal. That was your stats 1 stuff. Most of stats 1 we don't really talk about. The T is a modified normal. It's actually modified the other way. It's going, but so the T, the variability in the T depends on the degrees of freedom, which is related to the sample size. Then we last module we did the chi-square. Now that's a crazy one. The chi-square is a whack job because it's different for all different group sizes and sample sizes, and it's hard to track. The F distribution is even worse. It not only has one degree of freedom involved, it has a numerator and denominator degree of freedom. So the F distribution, there's literally like a gazillion of them. It's not like the normal when we talk about the standard normal. But the important thing for you is that this is the distribution your test statistic comes from when you do ANOVA. And that's really all that's important for you. Um, it's also not symmetric, so it's sort of like chi-square. It does not have negatives, it's strictly positive. Okay. It's not at all like the normal or T. The normal or T, you have positive and negative territory. The F and chi-square distributions, you only have, and they both are, the F distribution actually, it uses square metrics as well. So the F distribution is never negative. This axis here, the values of your critical values and test statistic, always positive. Okay. The exact shape depends on two different degrees of freedom. So you actually have a case, this is going to be a ratio. So the numerator and the denominator have different degrees of freedom. And then you have like this 2 comma 3, and then you have like two separate degrees of freedom to base the distribution on, which gets a little beyond what we actually care about for this class. Okay. So the F distribution is a continuous probability distribution. What it does is it arises from the ratio of variances. This is in part where this analysis of variance name comes from. Okay. It has a numerator and a denominator degree of freedom because it's actually going to be a ratio of variances. So we have a variance on top and a variance on the bottom, and each of these has an associated degrees of freedom. And so there's actually a combination of them. That makes it sort of difficult. Remember my stories about the old days and the gazillion paper tables and statistics books and why everyone hated statistics? That's why. Okay. So I'm going to keep this mostly conceptual, but I do have to tell you like the foundational concepts so that at least you've seen this. Okay, so this is an example of the S distribution. I believe it's from one of my old Triola books. I don't know. Thank you, Triola. Let's accredit them. It's probably not a book that's in print anymore. This is an example of an F distribution. The axes values along here vary depending on what your degrees of freedom are. Again, though, we have the concept of here's your 95%. This is your critical region. This is your extreme 5%. It is always strictly to the right. And if your test statistic is in here, in the critical region, your p-value is less than 0.05, and you have a significant result in the case that you will reject your null hypothesis and you will be supporting the alternative. Okay. Here are some specific examples. I have literally no idea where this figure came from, so sorry. This is what this 2 degrees of freedom is, the numerator, denominator, and then you have like this permutation of different degrees of freedom, which can drive you crazy if you start thinking too hard about it. And so this is just an example of like different F distributions, of which there are an infinite number. And like, but you can see though, for different F distributions, where the extreme 5% would be, like your position of where the 5% area is going to change. So the critical value, which as you remember, that's a function of the distribution. That doesn't come from the data. That's where on the distribution itself, not accounting for anything relating to collecting data and calculating a test statistic. That critical value marks off the 5%, but the actual number here is going to be different for different F distributions. So it's not like the normal where 1.96 is the cutoff and you're good. It's like all over the place. Okay. So, yeah. So I don't want to talk too much about the F distribution, like just other than you should know that it is the distribution that ANOVA is using to get those test statistics. Test statistic, remember, is the one from the data. That's this. Your test statistic is always a function of your data, and it's also a value on the F distribution. The critical value is the 5% cutoff. That's a set feature of the distribution. And so the area associated with the test statistic is the p-value. Okay. Same sort of game, different players, right? Okay. So now we have a blurry example that I don't really exactly remember. Oh, this is just to show you what the old tables look like. Nightmares. So you have like rows of degrees of freedom and columns. So if you're looking for like 1 degree of freedom, 1 degree of freedom, that would be here. If you're looking for like 1, 2, it would be here, or 1, 4 rather. The F distribution is a ratio, and this is actually a little bit important. It's variability between over variability within. This is what's called why it's called the analysis of variance, because we're using variability, which remember does have the mean in. We're using variability to calculate our test statistic. That's why it's called the analysis of variance. Even though we don't really care that much about variance, we're looking for the difference in means. Okay. It's weird. I know it is. I didn't invent this. I'm just teaching it. Okay. One thing about ANOVA that you should definitely know and we'll look at is it's all summarized in this thing called the ANOVA table. And ultimately, what really matters in the ANOVA table is at the end, my pen's through, you have the F thing. This is your test stat. And this, of course, has an associated p-value. Really, you know, we mostly care about reading this, and we will get the associated p-value. And then, of course, the p-value less than 0.05, we have a significant difference rejecting the null, and p-value greater than 0.05, we are basically supporting our null hypothesis. All of the technical junk in here we're going to look at briefly, but I really don't want you to like study this too much. It's this n value. But the reason this table is set up this way is, well, first, it kind of comes from the old school before computers kind of thing. We could do this. These are like all the interim calculations you need to get to here. Are we going to do all of this by hand? No. I'm going to show you some of the examples. I'm going to show you one in sort of gross detail that I'm actually going to cheat and give you the Excel stuff from last year. But you know, it's sort of like this is the kind of stuff where you can be like a giant time suck and thank goodness for SPSS and its generous, wonderful support helping us on this. Okay. So this is an important conceptual thing. Pay attention to this. It's cute and fun. I went and borrowed pictures of dogs. I myself have a golden. He looks kind of like that. I think my dog's better looking in a different way. But anyways, so let's think about dogs, and you're like, why? Let's see. Dogs, like breeds of dogs. We're talking about. We have to talk about like purebred dogs, not like mutts. Sorry, mutts. I like mutts. I do. But we're not talking about mutts. We're talking about purebreds. Purebred dogs like are vastly different in size, and you would expect for most of them. Some of them I think come in like mixed, like poodles. I think you can get in different sizes, but like Goldens are like sort of medium large. These guys, I think they're Chihuahuas, are like these tiny little things. Beagles, I don't know. I don't know if I've actually seen many beagles because they used to be popular, but I don't know if anybody has them anymore. So beagles, beagles are kind of medium sized. But anyways, different groups of dogs have different average weights. Like the average weight of a golden, I believe, is about 65 pounds. Mine's a little bit bigger than that. The average weight of a Chihuahua is maybe 6 pounds. Maybe the average weight of a beagle is like, I think they're like 40. I don't know. I'm taking a guess. I'm not gonna look it up. But anyways, so the different, like, you know, within the group is the breed. Okay, within the group, there's like variability, but it's not huge. Like most Goldens are going to be between like 55 and like 75, I think. Most Chihuahuas are going to be, I don't know, not a lot of people have Chihuahuas in New Hampshire because it's freezing cold. It's not the greatest dog to have here. No offense. I don't know how you walk a Chihuahua in the snow, but anyways, but within each dog breed, there's not a ton of variability, but there's a lot of variability between the dog breeds. So we talk about within and between. Those are actually important concepts here. This F statistic is calculated by the variability between and the variability within. What it's looking for, okay, remember this is a test on mean. So if you have a big variability between, like we do with dogs, you get a big F ratio, not an F. And so this, because it's a ratio of this, if you have a big number on top, you're going to have a big ratio as long as the number on the bottom is smaller. Now, within, okay, that would be like within dogs. So with dogs, the variability between is going to be a lot bigger than the variability within, and you're going to have a big F ratio. I'm just totally making numbers up here. But when you have a big F ratio, what it's going to do is it's going to show a significant difference between groups, because if your F is big, it's like way out here, and it's got to be in that 5% range. So you're going to have a less than 0.05 value. So you're going to have a really substantially difference between the groups. That's how ANOVA works. Let me talk about that once more. So we have for dogs, there's not going to be a lot of variability within the groups, but there's going to be a lot of variability between. So if our question were the null hypothesis of there being difference between mean weights of dogs, okay, Goldens, Chihuahuas, Beagles, the null would be that, and then the alt is just that there's any difference. We're going to talk about that, but it doesn't, like, we're not talking about any specific difference. We're just talking about like a difference across the board. So what the F ratio is doing is it's looking at the ratio of within and between. Okay. The bigger the within, the bigger the F ratio. I mean, I did backwards, sorry. Between over within. Okay. Big variability between corresponds to the situation. There's going to be a big variability between the different groups. There's not going to be that much variability within. That gives you a big F ratio, a big and significant F ratio. And that's what ANOVA is doing. It's looking for that big and significant F ratio where the between variability is much bigger than the within group variability. Between means between the different dog groups. Within means within the dog group. So there's not going to be like, if we measured these guys, we get a relatively small variance because Goldens are Goldens and they're kind of inbred a little bit. So they're like sort of like all the same size. Cool. So that is the general concept of ANOVA. On the contrast, if we did cat breeds, yes, there are cat breeds. I don't have Siamese, I have Tonks, but they're kind of close. But cats, even if they're, I mean, unless you're doing like super extreme cats, like the giant savannas and like some miniature cats, what's going to happen with cats is that your F ratio is probably not going to be significant. Because if you do between over within, they're both going to kind of be like the same. I mean, it really wouldn't matter if we just pooled all the cats together. You're not going to detect like you did for dogs. You're not going to have like this group weight being way bigger than this group weight being way different than this group weight. You're going to have fairly similar ones, and you're not going to have a big F ratio. And so your p-value is not going to be less than 0.05, and you're not going to have a significant difference across groups. That's what ANOVA is doing. It's essentially doing like a signal to noise ratio. The only time you wouldn't even, you can have a very big between if for some reason you had a lot of variability within as well. Like if you have mixed breed dogs, that would happen. But we're not talking about mixed breed dogs, so don't worry about it. Then your signal would be strong, but your noise would also be, so your F ratio would be diminished. But typically with ANOVA, you're going to see that the difference between the groups ratio within groups, and you can detect a difference in the means by that ratio of between groups over within being large, which is what the ANOVA test does. Phew, we just learned all about ANOVA. How about that? Cool. Okay. And that's what this says. This is in the Blumen text that we kind of follow, but the slide material is largely from there. This is also what's called a one-way ANOVA. Now, for now, that doesn't really matter because we don't have a clue what a two-way ANOVA is. We will soon, don't worry. So this is a one-way, and what we call is a factor, and so this would be the weight of either cats or dogs. No, sorry, this would be the breed. Okay. A factor is kind of basically another name for a categorical variable. In AI now they're being called features. Even I get confused because like people are kind of like renaming the same thing in different ways. I don't know. I mean, it's how many names do we need for the same thing? Let's just call them categorical variables, but they're called factors. That's a typical terminology for a categorical variable when you're doing sort of more advanced statistics. So it's comparing the means of 3 or more groups. Typically, we don't want to do like 100 groups. So like for your project, please don't do like 50 different groups. You have to bend and consolidate that a little bit. Typically like 3 to 6 groups is a good number. After that, things get a little bit busy. You can do them for as many groups as you want, but it's mostly a practical test for comparing like more than 2 groups, but not like a gazillion groups, I guess. Okay. Okay. Here we go again. This is literally saying the same thing, but it's in verbiage. You can read this. The between group and the within group. I actually think my explanation makes a lot more sense than theirs does. The theoretical assumptions, again, always in statistics, and if this were a more advanced course, we'd spend more time looking at the specifics. We do assume the normal distribution from the sampling. Central limit theorem applies there as well because we're looking at means. Samples must be independent of each other, meaning that you can't have like the same dog in the Goldens and the Chihuahuas. The variance of the population must be equal. This one is a little funky to understand. Um, so we're not actually going to look at that, but that was a little different. And the samples must be random samples. Okay. Randomization, unbiased data, we're always trying to analyze that. For this class, we want to teach the concepts related to analyzing data and stats first and foremost. In grad school and stats, I sat there and went through minutia details and things like that. And if you're publishing, if you're going to do a professional publication, you want to consult a statistician and make sure that all of your test and all of your data complies with all of the formal statistical assumptions like this, and do a much more like just in case you're missing something and you're accidentally running a test where there was some type of dependency or something that you didn't notice. So we're a little sloppy in this class for time and the focus of the course, but there's always in statistics and formal analysis, formal assumptions and things that need to be looked at in terms of fine tuning. Okay. So here is the prime example. This is from chapter 12 of Blumen. As usual, and I don't like this. I absolutely hate this, but it's textbook land. Here is our sample that has 4 small cars, 5 sedans, and 3 luxury cars. So we have a whopping sample size of 12. Please don't ever do any serious analytics on 12, please. But anyways, so what they're trying to show is miles per gallon. They like to, I do like the really simple, like everybody can understand it exampleness of this, but like 12 is not research, people. So they're trying to determine if there's a difference in fuel economy for 3 different types of automobiles. Okay, that's the test. MPG for small, MPG for sedans, MPG for luxury. Okay. The null hypothesis is that the mean is equal for group 1, group 2, group 3. It's kind of arbitrary which one was 1, 2, and 3, but so they're saying that the mean of the small is equal to the mean of the sedans is equal to the mean of luxury. I mean, if this were a 2 sample test, we would have just done like 2 of them, but now we have 3, so we're into ANOVA world and we're testing the difference. The null hypothesis is that there is no difference between the mean of the groups. Okay. The alt is strictly that one is different. It doesn't matter which one. We are not, be careful. We are not testing this. They don't all have to be unequal. It's just that one of them has to be unequal. Okay. So there has to be at least one that's different from the others. It could be that like you have 10, 10, and like 35. Okay. And then this would show that this really only this is the group mean that's way off. These two are actually equal. So it's not actually testing that they're all different. It's just testing that at least one is different. That's kind of an important part. And then they talk about the F distribution and how it relates. Now, the 2 degrees of freedom that I sort of don't really want to talk that much about because it confuses even me. We have a total sample size of 12. There are 3 groups. So the numerator degrees of freedom is 2 and the denominator degrees of freedom is 9 because we do the numerator degrees of freedom is simply the number of groups minus 1. That's always understandable because you have like 3 groups, 4 groups, you can figure that out. And then the denominator degrees of freedom is the sample size minus the number of groups. That's where you get the critical values. The critical values don't come from the data. This is the value that's part of the distribution. This is the value that marks off the 5%. We don't need this when we do work in SPSS, and SPSS does not, in fact, even give you this. You can't even get an SPSS if you want it. You have to go look it up in an old table. But that's what this is actually doing. And then the test statistic compared to the critical value. But we generally will just use the test stat and its associated p-value. Critical value is always associated with 5% or whatever other, it's going to be always 5% for us. Test statistic, the p-value is what we actually are using because that's the stuff that comes from the data. Okay. Now, if you want, and I really don't because I'm just not feeling it. I don't, this way, they're actually going and doing the old school mathematics and they don't show all the details in Blumen either, even though they cover like a couple pages of this. Calculating, what they're doing is, okay, I will go over this slow. For each group, the mean and standard deviation. So, I mean, there's only 4 small cars and like 5 looks, So this is the absolute maximum number of data values that I could ever even like stand to look at by hand. But so they have here, you know, the small cars. And then we have this thing called the grand mean. This is what you would have done in stats 1 if you just had like all this data here and like not like if you just had this and not even grouped. That would just be, this is your overall mean. Okay. And then they're calculating what they call the between group variance. This relates to the numerator and denominator of the F statistic as well. These particular calculations, I don't want you to worry too much about. They're in that table. We're not going to hand calculate them. They're going to be in that ANOVA table when you get your SPSS output. This thing, we're going to be able to interpret this. So what these calculations are doing is they're calculating all of these and all of these and then all of this. Ultimately, you get your F ratio out of this, and this is what we're going to look at, our test statistic F ratio and its associated p-value. All of this other stuff is sort of like mathematical minutia. We're going to look at one example done out a little better than this. What I don't like about this is I like to do it in a table, and this is like done as like all kinds of little rows and calculations. But ultimately, when all is said and done, finally, Blumen gets to the actual calculation of this F statistic. Phew. And this has 2,9 degrees of freedom, if you were paying attention to that. I don't know what a 2,9 degree of freedom F distribution actually looks at. So somewhere we get this test statistic of 4.83. And the question is this in the extreme 5%, yes or no? And the answer is it depends a lot on what the F distribution you're working with is. That's why that degrees of freedom comes into play, because the F distribution is not generic. There's not one of them. And I don't know where 4.83 would be off the top of my head because F distributions are too complicated for me to just guess. Oh, here it is. Okay, so here it is. They drew it for us, thankfully. So this is the F distribution with 2,9 degrees of freedom. And if you looked it up in a table, and I believe the tables actually are in Blumen, good luck. This is our test stat. This is this, that all of these sort of like little nitpicky calculations got to. This is the critical value. This is the one that I said you can't get this in SPSS. This is your like equivalent to 1.96. So for this is the critical value marks off 5%. The test statistic here is clearly within the 5%, so it's going to have a p-value less than 0.05. And we are in fact going to have a significant difference in gas mileage from, I forgot, small cars, sedans, and I don't know what it was, luxury cars. Okay. And so that is the conclusion. Now, what I don't like about Blumen is there's no p-value, which is kind of a nightmare because it doesn't tell us, like, Blumen just gives this. Not that we really use Blumen that much. But what this is doing, it does all the interim calculations, and all of this is done to get to here. Now, these right here, this mean square, this right here gives you the test stat. Okay, so you have to calculate these, and these. Basically, this is just the sum of squares, which they were actually, this is just like, it's the data values minus the means, and then like the group mean minus the, we're going to see one of these, but I'm not going to account you for doing it. But you need these, and then the mean square is actually just 242 divided by 2. It's just a division going on here. And then the F statistic that we actually do care about comes from the division here. But we also want to have an associated p-value. Now, SPSS will have that because the only way we can figure out whether this has a significance is to have that p-value there. But Blumen doesn't put p-values in. I don't know. It's old school. Anyways, phew. So we're ready to do an example in SPSS, but guess what? I'm going to break this video and start a second video for that example, and then start the next video with that example. Okay, good.